In this lesson, we'll be talking about the definite integral and how it is precisely interpreted. So in a previous lesson, remember that we said that the definite integral was actually just area, so long as the function was positive. So let's take a look at this definition again. And remember, the way that we set this up was we looked at rectangles, and we took the function height to help us find the height of the rectangle, and then the delta x was the width of the rectangle, and when we added up all of these areas and let the number of rectangles go to infinity, that's how we defined the definite integral. But what would happen if this function were negative? When it's positive, it's clearly just area. So let's take a look. If the function were negative, this value would be a negative number. But delta x is the width of the rectangle. That's always positive. So when we multiply the function times the delta x, that's a negative number times a positive number, and so I'm going to get a negative number associated with one of these rectangles. So what that really means is when the function is negative, I'm really still talking about area, but I count the area as a negative number. So let's write this down. The area of each rectangle counts as negative, so the definite integral represents this negative area, if you will. And we'll take a look at that in our next slide. So here's how this actually works. If we have a continuous function, which is just part of the definition of this definite integral, then what we can do is we can look at our integral here, and what we're going to get is this is the sum of all the areas between a and b. But when I say sum of the areas, it's sort of a net sum, if you will. If the function's positive, then the area is positive. If the function is negative, then the area counts as a negative number. So let's take a look at this example. We've got this function x cubed minus 7x squared plus 12x. And we want to figure out the area under the curve based on this integration. So what we're going to do first is just draw the graph of this. You can use your graphing calculator for it, but I'll just go ahead and show you guys what the graph looks like. Let me go by a scale of 2 on my y-axis because this graph goes kind of high. But I'll still go by a scale of 1 on my x-axis. So what this looks like is something like this. It goes up to 6 about right here. It comes back down to 0 at 3, and then it has this small loop as we go to 4, and keeps going to infinity. With that said, what we're interested in is finding the area under the curve from 0 to 4. Now when I say area under the curve, remember this is really a net area that we're talking about. So what I'm going to do is I'm going to use my calculator to calculate this integral. But because of the fact that I've got a positive and a negative region, for now I'm actually just going to calculate the integral from 0 to 3. Use the technique that we talked about last time to calculate the area from 0 to 3. And feel free to pause and give it a try before I give it to you. For this region, I have a positive area. Remember, it's just the area under the curve, which means the area below the curve but touching the x-axis. I get 11.25 for this area. Now let's do the area from 3 to 4. Now because this area is below the x-axis, it's going to count as a negative number. Now even though that sounds strange, just keep in mind that the definite integral does sometimes interpret areas as negative numbers. Anyway, go ahead and try to put this in your calculator as well, this time only doing the integral from 3 to 4. When I do that, I get negative 0.58, and it's got a bunch of 3's, but I'll just round it to 2 decimal places. So with that said, the value for the integral from 0 to 4 of the whole function here, x cubed minus 7x squared plus 12x dx, is going to be the sum of these two areas, 11.25 plus negative 0.58. I get 10.67 as my area in some respects. It's not exactly area. Remember, this is the idea of the definite integral. The definite integral considers areas above as positive and areas below as negative. One thing that we could do is we could have just integrated from 0 to 4 from the very beginning, and that would have given us 10.67 as well. However, one of the things that we got by doing this is that we can see how the positives and the negatives fit together. So then we've got the second question. What is the actual area of the region between the function and the x-axis? So this area we counted positive, and this area we counted negative. If we're talking about actual area, there's no such thing as negative area. So I will give you one example here, and in the future, this whole actual area concept we won't do because I don't want to confuse you in the future. Regardless, the actual area is going to treat everything as a positive number. So the actual area will be 11.25 plus 0.58. This time we're treating everything as positive when we do this. And we get 11.83 is the actual area. So again, the actual area means that all the areas have to count as positive, which you do have to be a little bit careful on your calculator to do. However, we will not be doing very much of this at all. The next example represents something that's a great idea for us to be able to do. So what we have is 3 different problems, and we want to decide if the value of the integral here is going to be positive, negative, or about 0. And keep in mind when I say the value of the integral again, we're talking about this signed sum of areas. So negative functions mean negative area. With that said, here's your first example. We've got this little tiny region of positive, and we've got this very large region of negative area as far as the definite integral is concerned. So I think it's pretty clear here that the negative area is much larger than the positive area, so overall the integral, not the area but the integral, is negative. Let's do that again. For this region, we've got all this positive area above and a little bit less negative area below. So because the positive region is larger than the negative region, we have a positive integral altogether. And in the final example, we've got this positive region, and the negative region looks like it's probably about the same size. So since it's about the same size, we're going to say that in total, you've got this positive area plus the negative area being about the same. They're going to cancel each other out and leave us with about a 0 area overall. Now keep in mind this is a 0 integral. It's not really area, but we're going to be thinking of area from now on as positive or negative. The next concept is the area between two curves. The area between two curves basically is just a new formula. If you want to find the area between two curves, you use this formula f of x minus g of x. And to be a little bit specific, we always look at it as top minus bottom. That's where you see that we have that the function f of x is bigger than the function of g of x. So you'll always take the top curve minus the bottom curve. And this is pretty easy to put in your calculators as well. For example, let's take a look at these two curves here. We've got 4x minus x squared, and it might be nice if I label that as this one, the parabola shape. And g of x is this 1/2 x to the 3/2. The first thing that we might want to do is figure out where these two curves intersect. And though there's no way that I can show you this on the calculator right now, we can definitely do this in class, and I can give you this example. I'll take you through the steps. You would plot both of these functions in your calculator. Give it a try real quick and see if you can do it. Now that you have the two curves graphed, we're looking for this x value. What you'll do is you'll look for the calc menu that lies above your trace button. So if you're looking at the graph of these two functions, you can hit second trace and that will pull up the calc menu. From the calc menu, look for the Intersect command. The Intersect command will give you the ability to look for the intersection between two curves. What it'll do is it'll ask you for the first curve, so just pick that one and hit enter. Then it'll ask you for the second curve, so pick that one and hit enter. And then it'll probably ask you for some sort of guess to find a center area. If you do that, you find the intersection between these two curves. I get about 3.12 for my intersection. With that said, my integral is going to be the integral from 0 to 3.12. And again, the formula is top curve minus bottom curve. Notice that I used a lot of parentheses here. It's a good idea to put parentheses around the top curve and around the bottom curve just to be safe. And then the whole set of parentheses around the outside is what I was telling you guys about for just good notation here. So what you can do now is put this into your calculator and get a value for this integral. Give it a try and see what you get. My answer comes out to be 5.91 approximately.